Hello and welcome to this course, Basic Machine Learning, Shallow Learning. First of all, I want to thank you for tuning in on my course, and I'm very excited that you want to join me and the other students on your journey to becoming an expert in machine learning. This is a basic course for you who has not yet experienced machine learning or tried to develop real applications. So we will be going from scratch, talking about theory and into implementation, where we will try out different algorithms using an open source framework, and then we will discuss the pros and cons of each approach that we are using in this course, and then what you need to be aware of when you are taking your algorithms into a live system environment. So, first of all, what is machine learning? I have taken this sentence from Wikipedia, which sum up machine learning really well. It says machine learning is a field of computer science that uses statistical techniques to give computer systems the ability to learn. So machine learning is really a mathematical thing where we use mathematical forms and algorithms to take some input and turn it into an output, meaning that our computer will in some way learn based on what we have given it as training data, and then help us provide an output that in a given setting matches the thing that we as a person want. So most of the algorithms that we see today in machine learning is really old mathematical formulas that has now been tested in a new context and has become very popular due to the fact that they are actually able to provide us with a way to get our machines to learn based on previous experience, meaning that we can give data from previous experiments or cases, and our mathematics will use those to provide predict new outcomes for a new setting that it is seeing based on previous experience. So where is machine learning used? Machine learning is in today's world used in almost every major tech service out there. You have probably been using Netflix before, or Amazon, or some of Microsoft product, or most likely you have a Facebook account. So if you have been in contact with any of these services or many other services out there, you have been experiencing machine learning. Machine learning is under the hood of these IT services and is used to make their service even better. Netflix, for example, uses machine learning to predict movies or series that you will probably like, meaning that they can get you to use the service more because they will recommend things that you like, and thereby you will be clicking it and spend more time watching because you actually liked what they recommended to you. Amazon is also using recommendation algorithms to try to predict what you are going to buy and what you may like based on previous purchase logs. And also Facebook tries to use machine learning to predict which friends is maybe in your neighborhood, or is you most likely to try to connect with, or what posts will you be likely to engage in. Will you like these posts, or do you not like a given topic, and thereby are not very likely to interact with these people? Then they will try to sort them out. And also Microsoft, as one of the largest tech companies in the world, is using machine learning in almost any of their products by now, because machine learning can be used in so many different contexts and in so many different approaches that it is basically up to you as a software engineer or developer to try to fit it around a given product to make it even better. Also, customer service has been a popular field for machine learning in recent years, because you can use machine learning algorithms to answer basic questions that your customers may be asking, such that what is the opening hours, how do I complain about a given product or service, and the algorithm can answer by itself based on what it read out of the sentence that you are writing, and then they can cut down on customer employees, because the algorithm can take care of most things. Also, it can be used to automatically post on social medias for digital marketing. You can use algorithms to do such things and try to predict what your customers will engage in. And there is a lot of settings and in context that machine learning can be used, and we have not yet seen the top of it. We are only just getting started, and it's therefore I'm excited that you want to get into machine learning and maybe come up with a product on your own that can help users out there in some great way.
Hello and welcome to Venslov Academy. In this video we'll be looking at underfitting versus overfitting, because this is a really important topic within machine learning when you are to choose a model based on the data that you have available. So what is underfitting? Well, underfitting is when you have a high bias within your data. So you are basically oversimplifying the problem, which is not doing very well within your training set. So for example, on this graph right here, we are oversimplifying the problem by just taking a linear approach and just take a line straight through our data and say, okay, that fits kinda okay. But as we see here, we are not really categorizing these into the colors, because we have a lot of red dots on the top, which seems okay, but we also have the same amount or on the bottom in the blue area. So by oversimplifying this problem, by just categorizing them like this with a linear approach, we are really underfitting right here. And an example of looking at the underfitting problem in a bit more simplistic way is by looking at this categorization problem here. So here we have some objects that we want to categorize. So on the right we have a category called Lego, and on the left we have no Lego. But the problem here is that, well, this seems fine for the right side because all this is Lego, but on the left we also have this Lego minifigure, which is actually also Lego, even though that it is not a Lego brick. So the house and the car is correctly categorized, but we are failing on this particular object here. So a better approach based on this data is to make the categorization of Lego bricks versus not Lego bricks, because then we are not oversimplifying it by taking this large term, the Lego, when we are not seeing anything else than Lego bricks. Why not use the category Lego bricks here? Because then we can just say that everything that is not Lego bricks, which is actually all that we have here, could stay in this category. And right now we are having a much better fit based on this problem. So if we are to look at overfitting, which is compared to high bias, is high variance, it will look like this. So compared to underfitting, we have overfitting, which is, instead of high bias, we have high variance. And here we really try to overcomplicate the problem more than necessary in order for us to perform very well on our training set. And for example, we see right here, instead of having this linear approach, which we had in the underfitting example, we here try to match the data exactly. So we just basically follow the blue points around here, and also in this corner case up here. So one could imagine that, for example, if we now trained our model based on this, we get a very good result based on the training set. But when we see new data from the real world, we could probably also have a blue dot right here, or we could have run one right here, because it is very near to the other blue spots. But because our model have kind of learned the way of the training set, it will get an error on this, because we are actually saying that this is out of the area where it is supposed to be in order to be blue. Oh, I see now that this is gone around, so this should be cornered off right here, of course. So just a bit of a drawing error, but you get the example. So if we take this back into our little categorization problem, we see here that now instead of, for example, saying Lego bricks, we want to complicate this. So now we say Lego bricks with only 4 studs, and on the other side we have not Lego bricks with 4 studs, and that is still valid because we only have these Lego bricks right here with which all have 4 studs, so the 4 here on the top, and on the other side we have no Lego bricks with 4 studs. But if we then trained our model based on this and moved it out to the real world or got some new data in, we could imagine that we, for example, got this data point right here. So that will probably get within this right side of the graph, but because that we have complicated our problem, which before were only Lego bricks, this is now an actual error because this is not a Lego brick with 4 studs. This actually have 8 studs, so this should belong to this side, even though that is still a Lego brick. So here we have overcomplicated the problem. So what you want in machine learning is basically to get in between. So instead of underfitting, as we see here in the top, where we just have no Lego versus Lego with the linear approach here, you want to be in between this underfitting and the overfitting, which were complicating the problem even more with adding the 4 studs and trying to match the training data as closely as possible, but you want your model to be in between based on your data. So here we have taken a more loose approach, but not loose enough to having it underfit and not tight enough to have it overcomplicate itself by overfitting. So here we are taking this line, for example, right here. So even though that we see that we have a red dot in here and a blue right here, we could imagine that if we got new pieces in, for example, this Lego brick right here, this could, for example, be within this place here, but this model here has a lot of errors and are missing a lot, and here we will again miss it because if it is placed right here, it will be out of this model that we have trained here. So in machine learning, you really want to be in between overfitting and underfitting, and that is really hard and take a lot of practice to do.
So in the text, in the title of this course, it is shallow learning. So it's natural for us to discuss shallow learning versus deep learning. So basically there are these two forms, and it's more like buzzwords than actual computer science terms. And shallow learning is what we see in the picture on the left, where we have our input, and then we have some hidden layer, and then we have our output, meaning that we can give our input, for example, users rating or previous purchase on a site, and then our algorithm will, in this single hidden layer, try to predict based on a mathematical formula what you might predict other items similar to that, and that will be your output. So this is what is basically mentioned in the industry as shallow learning. Very simple algorithms that can take an input and provide an output, whereas deep learning is the more advanced stuff. This is where Google's open source framework TensorFlow is top in the industry. Deep learning is more advanced, and we will not be touching upon that in this course. So when you have a fully understanding of the basics and you wish to go a bit further, then I definitely recommend you to find a great course in TensorFlow and try some of these algorithms out yourself. Deep learning is where you have an input and you maybe don't know what features this input have, and the mathematics will try to figure it out itself, and then have many layers, even hundred of layers, that take a look at this input in different directions, and then in the end try to predict a final output. So you don't just have one layer that says, okay, what is the similarity between this, but your what can we say, your item or your input will be looked at in many different ways, and based on all these layers and all the nodes in these layers, final summarization of the algorithm will give a final output. So this is the more advanced stuff, but in this course we will keep it to the basics in order for everyone to get along. So we will be focusing on shallow learning. And then the framework. And as I mentioned, Scikit Surprise framework is the framework that we are going to use in this course. We will be looking into KNN, K nearest neighbor, and SVD, singular value decomposition, which is two shallow learning algorithms that is very easy to implement and is fairly easy to understand. So these are a great example and a great tool for us to play around with. And then on the other hand, we have the TensorFlow by Google, which is based upon deep learning and neural networks and much more advanced stuff, which we will not touch upon in this course. So, theory versus practice. MI takes time to get good at. There is no shortcut in getting to becoming an expert in the field of machine learning. And even though that you take this course or you may take another course, you will still find yourself out in the dark, because this is such a huge area that people take many years to get good at. People take PhDs and university degrees just in focusing on MI to get good at this. But before you get started, the better, because you just need to get started in order to be good at something, and then you just need to practice and practice and practice. So why theory is not enough. You can read and study all you want upon MI and read all the books that you can find on the topic, which is of course a great thing. Reading books is good, and you should definitely do that in order to become an expert, but it is important that you do not forget the practical approach of MI, because when you read in the theory, I have experienced that myself, I understood the topics, and I said, okay, these algorithms are really smart and they can be used in this context. But then when I had to implement them in a physical setting where I actually had a live system, then I suddenly found myself in doubt, because what I thought was a good approach to use suddenly were not the best approach, because in this given setting, this algorithm that I was implementing did not suit the context, because I had a live system where I needed to recommend some items to users, and the algorithm that I chose, it gave me the best result when I tested it, and it was great on paper and when I read about it, but it had to train and train a model for itself, meaning that it had a pre-trained model where the predictions and so on for all my users were laid out in a file that I could look in when I needed recommendations. But when a new user got created in the system, he was not part of that pre-trained model. So suddenly the new user, I was not able to recommend anything to him. So I had to find another approach to give him recommendations when he was new to the system. So this is an example from the real life, where you, even though you have the understanding and you have read about it and you have a plan, then suddenly when you test it out, you find that your plan does not work as expected and you need to change. And this is really where you learn in machine learning, because you will find yourself in these kind of situations all the time, because it's really a tricky thing, MI, and you need to do these practice implementation a lot before you get used to what works and what do not work in a given setting. But now it's time for us to get started. On the front page you will have an overview and a basic introduction to what this framework actually is and what kind of algorithms that it contains. It is, as mentioned here, a Python library for recommender systems, meaning that all the algorithms that you will find in here is basically recommender algorithms. Recommender algorithms are where you give an input, typically users and items, and some ratings that these users have given those items, and then the algorithms are capable of predicting what kind of rating the users will probably give to the items that they have not yet rated, meaning that these algorithms could be typically Netflix algorithms that can be used in the context that Netflix is operating in, the movie recommendation, or in the context of Amazon, where you recommend items in a store setting. And some of these algorithms are actually, well, have actually been used in some of the world's most popular services. So it's a Python framework, meaning that of course we are going to be writing Python code in this course, and I'm looking forward to do that with you. And then we will be evaluating based on what is called fivefold cross-validation, which is a very famous way of validating our algorithm within machine learning in a computer science setting, because we will split up our results in order to get a calculated score of how well our algorithm performed, meaning that how far did we miscalculate. So if a user has rated an item with a rating of 2, then if our algorithm rated 1 as a prediction, then we were 1 rating off for that particular user. But we will be talking much more about the evaluation part in the next lecture, before we start by creating our Python recommender skeleton, which will also be in this part. I want to introduce the theory before we get started, because people tend to get too fast into the programming stuff and then forget about the theory, and thereby misunderstand the result that they are getting. So on this side you can see the different algorithms. They have been tested on 2 different data sets, which is the MoveLens 100K and MoveLens 1 million, and you have what is called root mean square error and mean average error, which is something I will explain in the next lecture. Then you have the different algorithms that this framework contain. What we are going to be working with in this course is KNN and singular value decomposition. So basically you can see here how this framework works, and you can dig into the documentary and then follow along, meaning that after you have completed this course, if you want to experiment with some of the other algorithms or see what else this framework is capable of, you can go into documentation and start to experiment yourself. There's a lot of different parameters that you can set, and your result will either be better or worse depending on the data set and what parameters you are using. So this is a really fun thing to do in order to really understand what is going on in the algorithms, because when you're playing with the parameters you start to understand why the algorithm react in a certain way. So in this lecture we will be talking about how to evaluate our machine learning algorithms, which is a very important part of the whole MI topic, because if you can't evaluate your algorithms, then you have no idea whether one algorithm performs better than another, and you are really blind when implementing the algorithms. So a major thing that is talked about in machine learning is accuracy. How accurate is your algorithm? And the accuracy can be viewed as we see on the screen here, that you take the number of correct predictions divided by the total number of predictions. So when you are predicting something that could be ratings that a user will give to item, then you just take the exact number of correct predictions, on meaning that the correct ratings that you have predicted, and divided by the total amount of predictions that you made, and that will give you an accuracy score. Then you can switch out your algorithm and keep the training data, and then you can compare your accuracy result and see how well your different algorithms perform given your data and the context that they are implemented in. Beside accuracy, a very popular way of viewing your error rate in machine learning is using what's called MRE, meaning mean average error. And the way that is calculated is as we see right here. And what we are basically doing in this mathematical formula is that we take our actual rating, so we have a test set, meaning that our users have rated some items, and then we try to use our algorithm to predict a rating for these items but we are here hiding the actual rating such that our algorithm does not see what the users has rated, and then we just train our algorithm on some training data that do not have these ratings within, and then when we have a prediction we can take the two numbers and compare them. So this means that yj here will be the actual rating, and then you just minus the predicted rating. So if a user has rated like the movie Jurassic World has giving that a rating of 4, and you predict a rating of 3.5, then you minus 3.5 with 4, and then you just do that for every prediction that you have, meaning n times, and then you just get a divided result, meaning that your mean average error is the error result of all your predicted ratings compared to the actual rating. So in order to do this, you need to have some ratings beforehand that you have hidden from your algorithm, because else this will not work, because then you just compare your predicted ratings on something that you have used to train your algorithm, and that is not a sufficient way of doing it, because you'll get an incorrect result. So it might look very complicated, but it is really not. But the surprise framework will do this automatically for us, and the way that it will be displayed will be using the fivefold cross-validation. So what is the fivefold cross-validation? The fivefold cross-validation is a way to extend upon the score that we just saw, the mean average error, because you can take the mean average error on your entire data set at once, meaning that you train on all your 80% is popular, so 80% of your entire data set, you use that for training, and then you hide the last 20% for test, which is the data that you will be using in your mean average error, so the rating right here. But when using fivefold cross-validation, we iterate over this 5 times, meaning that we will switch out the portion of our dataset that we will be using for training and test, such that we can train and test on all the data in our dataset. So in the first iteration we use the first 20% for test, and we train on the last 80%. Then in the next iteration we will train on this part, test on this, and train on the rest as well. And then we will get a unique MIE, or not unique, but a single mean average error score for each of these iterations. And at last, when we have iterated 5 times and tested on each part of the dataset, we will take all the mean average error scores and average them out, such that we get a total mean average error that is based on our entire dataset, where everything has been used for training and test. The reason why this is a very recommended way of doing evaluation of your algorithm is because if you take this first iteration and only look at this when evaluating your algorithm, you might be very lucky that the part that you have taken out for test in order to compare against your prediction is a very lucky test set, meaning that you will get almost everything correct, but that is only for this part. If you take any other part of these, you will have a very high error rate because you are not so lucky in these. But if you do not iterate and do this fivefold cross-validation, where you switch out test and train, you will not know that this is the case. You will just trust blindly on your mean average error score that you have received from this first iteration. So by doing this, we ensure that there's no lucky test set or some unlucky train data that in some way influences our result in a wrong way. So as mentioned, surprise, the library will output this automatically when we set it to do so, and the way it is outputted to us is in the console, as you see here. So we have the 5 folds, so we have fold 1, 2, 3, 4 and 5. Then we have a mean average error score for each of the fold, and then we have a mean for the entire test for the entire evaluation. So this is a really simple way of testing your accuracy of your algorithm, and the good thing about this is that we can get surprise to do this automatically for us. So there's no reason to sit down and be nervous now because you have to understand different mathematics terms, because we can start out by getting surprise to do this, and then when you are getting used to how to evaluate using this automatic tool, you can start to do these calculations yourself in order to understand it better, and then go beyond and look at other evaluation matrices as well. So this was all for evaluation. Now it's finally time for us to dig into some Python code, because in the next lecture we will be building our MI skeleton that we will use in the rest of this course. So see you in the next lecture. So before we get into the code, it's important that you have a Python interpreter installed on your computer. If you do not have one already, you can navigate to python.org and install Python. It's important that you download the version 3.7 for now. Maybe later on you watch this course and this version has changed, but the important fact is that you download a version of 3.5 or above, because the code that we're going to use will not work probably if you download the 2.x version. So navigate to python.org, find the right version, and simply just click download and install it on the given operation system that you have coding. We will start off in an empty project just like this. I have just created one and called it Basic MI Course. You can use any IDE you want, PyCharm, whatever. If you want to use PyCharm, which is the IDE that I'm using from JetBrains, you can navigate to PyCharm and then simply just download a 30 days trial in order to follow along with this IDE. If you don't want to use PyCharm or simply have used your trial already, simply just find another open source IDE for coding Python, and yeah, most of them are similar, so you should be able to follow along even though you are not using this one. So we will start off by creating a new file. So we will create a new Python file. We will call this recommender, and then we need to import the different packages that we are going to use. So we will say from surprise import SVD, from surprise import KNN basic, from surprise import dataset, from surprise import reader, and then we will say import pandas as PD. So what we're going to do in this lecture is the skeleton for our further sections. So we will be building the skeleton that we will be using in the two next sections, which is regarding KNN and SVD. So this will just be a basic module that we will create. And as you see now, these are highlighted, and we should see that unresolved reference because we have not yet installed the package needed. So we will navigate to our address project interpreter. You can install the packages for Python in your command prompt as well if you're not using an IDE but just a simple text editor. It should be the same. So the packages we are going to need is first NumPy. We are not importing anything from NumPy, but in order for us to install Surprise, we need NumPy installed because it has a dependency that NumPy has to be installed. So we will install that. When NumPy is installed, we will install Surprise, and it is this scikit surprise package or library. Once installed, we need one last thing, which is pandas. and this is the version right here. So we install this package as well. So once pandas has been installed, we can close this down and let the project refresh, and all the libraries should then be installed. So we will try to continue, and now we will be creating a simple test data set that we will use. The test data set is one I have just created out of pure imagination to make it easier for you to understand what is going on. We will also be using a larger dataset which is public available and can be seen on the documentation page for the surprise library. So we start by saying users, which is an array of our users. Then we have movies, and we have score, or let's say rating. So now we need to fill out these arrays. So as you might saw before, we have this table right here, and this sum of the values that we're going to put in. So we have 4 users, we have 3 movies, and the users has rated the values in the following way, the movies in the following way. So user 1 has rated Harry Potter 3 and Star Wars 1, but not yet rated Tomb Raider. And the same for user 2, it has 3 on Harry Potter and 4 for Tomb Raider, and so on. So what our algorithms are really doing is trying to predict the empty values, like filling out these empty values, because this is the things that we are interested in predicting. There's no reason to predict what user 2 will rate Harry Potter because he has already rated it 3. So what recommender algorithms is all about is filling out these missing values. So we will fill this in. So we will say users. There we have user 1, 2, 3, and 4. And then we have user 1, 2, 3, and 4. Because you need to, for each time a user has rated an item or a movie, it has to be present in this array. So if user 1 has rated 2 things, like here, he will be present 2 times. The other doesn't matter, as long as the place that user 8 is present matches the movie position right here and his rating right here. So if we go back, we see that each of these has rated 2 movies, therefore they are mentioned 2 times, and I have just made it in order for it to be more structured. Then we will say movies, and there we have Star Wars, then we have Harry Potter, and then we can just copy some of these. So we say Star Wars, and the next was Star Wars as well. Then we have Harry Potter, and then we had Tomb Raider, and Harry Potter, and Tomb Raider again. So now we have 1, 2, 3, 4, 5, 6, 8 movies, and if you look, these should match the table right here. You can pause the video and check up if you want. Then we just need to input the rating values. So this was 1, 3, 4, 2, 3, 4, 1, 1. So now we have 8 values in the user table, the user array, 8 movies and 8 ratings. So the next thing that we're going to do is making a variable calling ratings directory, which will contain all these values. So we will say user ID equals our users, item ID will be our movies. So this is basically a dictionary where the key is user ID and the value is the array of this users. So we will just match this up and say rating, and that should be the rating. So the next thing that we're going to do is make a new variable, and where we'll use the pandas library to make our data frame. So we say rating as input. Then we need the reader, which will define the scale in which our ratings go from, because our algorithm need to know, are we rating from 1 to 100 or what is the scale. So we will define that as being 0 to 4, where 4 is the highest value, and we just imagine that no one has rated a movie 0 yet. So now we just need to create the dataset based on what we have just defined. So we say data equals dataset dot load from data frame, and then we say df, and then we say user ID. This is the order in which they are coming in the dictionary. So we say item ID and rating, and then we need our reader defining the rating scale. So this is basically all we need to do in order to recommend something based on this small data set. And then we simply just create a new value called algo equals, and this will be empty until we continue to the next section where we'll fill out this value. This is just our skeleton, and then we will fill the last part out that we will be needing to move on, which is our validation, and we will be using the algorithm that we define, our data set, and we will measure based on mean average error, and we will be using 5-fold cross-validation as we discussed in the previous section, previous lecture. If you haven't yet seen that, please go back and be sure you understand what 5-fold cross-validation is and so on, in order for you to understand what this is really all about. So cross-validate, we forgot one thing up here. So we say from surprise, from surprise dot module selection import cross-validate. So this is our skeleton, and we are now ready to move on to the next section where we will be recommending something with our first algorithm. See our skeleton in place, it's time for us to start implementing an actual algorithm and do some recommendation. So the first algorithm that we'll be using is called singular value decomposition, SVD. So in order to use this within the skeleton we have made, we need to assign it to the variable algo. So we say SVD, and we can do so because we have already imported it from the start right here. If you haven't yet done that, just say from surprise import SVD. So now our algorithm is using, our application is using SVD. And if we go to documentation on the surpriselib.com site, you can see the different algorithms as mentioned in the introduction section. And we are using SVD, so you can click on the SVD algorithm and you will see all the technical stuff about this algorithm. How is the prediction made, what parameters are within this, and sorry, and what can you change, and what is the default settings of these parameters. So for example, we have the post that the number of iterations our singular our stochastic gradient descent will be using. This is a way our algorithm is trying to minimize the error rate using a gradient descent algorithm, and default for this is 20, and as you see here, the algorithm is by standard biased. So we can now go back into our Python application and we can try run this just as standard. So we will say run recommender. And as you see, it was pretty fast because our dataset is relatively small, and now we have our mean average error, and it is terrible. This is really a terrible value because if we go in here and we go a step back, you can see that on this dataset it was below 1 on the MRE, and we got like twice the error rate of this. And that is because in this dataset we have much more data. We have much more users and much more movies and a lot more ratings, whereas in this dataset we don't have much value about our users and their preferences. So for example, when we try to predict the rating for Tomb Raider for user 3, all we know is that he has some similarities with user 4, because these have both rated Star Wars, and then we only know that user 4 is rated Tomb Raider with 1. So there is not really a strong connection between these yet. But if we like took that they have rated 100 movies and we have a lot more users and ratings were a lot more connected, our MRE will certainly drop. And a way you can test this is by implementing the movie lens dataset. So if we just comment out this for 1, we can say that we want our data equals dataset dot load, and we say this one, and then we say ml 100k. So when doing so, we are no longer using our test data right here, but we are actually using this dataset right here that has been used for testing the framework. So we can now start the application, and it will probably ask us if we wish to download this, because we do not yet have this dataset in our project. So as you see, our MRE, mean average error, dropped dramatically, almost to half the size of what we had before, and this is starting to looking good. When you are using machine learning algorithms, you aim to get the best possible error, lowest possible error rate, not the highest, but the lowest, because that means that your algorithm is more precise and you are a lot better to predicting what users might have rated. So beside from using this dataset, we will just switch back to our little test set and see if we run this. We should be back at our terrible mean value, and now we can try to play a little with this. So we can say algo.biased equals false, and we can say algo.inEpoch and say 40 instead of 20. So this was true before and this was 20 before, and you can see all the different parameters that you can play around with right here and what they are doing, and see, and then simply just test yourself what works and what does not work, because machine learning is really a tickling game where you as you see here, this was terrible. We are almost at our error rate of 2, meaning that we rate way past our real rating. So this was certainly not good. Let's just try to remove this and see if it was this one. And yeah, now our mean average error dropped because we increased the stochastic gradient descent, meaning that it will loop over the gradient descent, which is our learning method, twice the amount it was set to as default. So you can really play around with these parameters, and now we actually have a good example of what I have been teaching you in the previous section about five-fold cross-validation and why it is so good. Because as you see here, our fold 4 and 3 is terrible folds, whereas fold 1 and 2 is relatively good compared to these two. So if I were just relying on this fold when I tested my algorithm, I will get a very terrible result. But overall, my algorithm performed better than this result right here, because in a mean I am at 1.2 instead of nearly 1.7. So it's Really important that you understand the different parameters you can play around with and try to tickle with them when you are changing dataset, because something works for one context and not for another. So that was all for this implementation of SVD. Now we will get a closer look at the actual theory about singular value decomposition. See you in the next lecture. Now we have implemented the SVD algorithm. It's time to look at what is really going on. So the SVD implementation is in this library has two different ways of being implemented. We have the biased version and the unbiased version. And as we saw in the last lecture, it is by default biased. So when biased, it is it's predicting based on this formula right here, and when it is unbiased, it is using this formula right here. It is important for me that you know difference between these two, and that you can change these. I will not be going through a long mathematical example here, because unless you really need to be a mathematical to explain this to someone in a mathematical way, it's not needed for you to know the complete calculation behind the algorithm when implementing it. But you need to know the different parameters and why they are acting as they do. We saw that our implementation had a very high error rate when using the unbiased version, when we set the bias to false, and that is true, and that is because we no longer use this formula right here, where we had a learning rate in our estimated formula. The learning rate is by default set to 0.005, and the learning rate is used alongside a stochastic gradient descent, which is the one right here, and the default, as we saw in the previous lecture, is set to 20, but we changed that to 40. But when using the unbiased version, this is stochastic gradient descent will not be used at all, because we will only take the dot product of these two tables, which is the table of items and the table of users, where the item table is transposed. So that was why we had such a terrible rating, because it's not trying to improve or anything. But if you use the biased version, where you will have this regularization term and a learning rate, it will try to optimize itself, meaning that we can loop over our prediction multiple times to try to get the best result possible. And we can then change this learning rate because it's a parameter as well. But as standard, it is very small, because stochastic gradient descent can be viewed as, if you look at this, we have the circles, and our goal is to get into the smallest circle from the outer circle. So what stochastic gradient descent is trying to do is, based on its learning rate, it is trying to reach to this lower area, meaning that we will decrease our error rate. And sometimes a high number of epochs, meaning that we will loop a lot of times over it, will be good in the context that we have and the data that we have. But in other times we don't need a very high value, because then we will just get into the middle and bounce in between this one and actually get a worse value. So again, this is a parameter that you need to tickle with each time you implement it in a new context and with new data. But normally you can stick with the standard or go a little above, like we did with the n epoch set to 40, and then it will try to get as close as possible to the lowest error rate as possible. So this was just a short theory introduction. I will be linking to a video where a mathematician will explain the calculation of the algorithm in a much more detailed way, and I really like the way that he does it, so I will not try to replicate his explanation, because I just think that the way he does it is fantastic. So you should really check it out if you're into the mathematical stuff. If you just want to be able to implement it and use the algorithm like you have done in the previous lecture, you're good to go, and you can keep on to the next lecture from here. Now that we have looked into singular value decomposition, it's time to look at another algorithm. This algorithm is called KNN, or K nearest neighbor. Again, you can navigate to the surprise lib, and under the documentation you can find all the mathematical stuff of how this prediction is made and what parameters you can play around with. For example, in KNN we have something called min k, meaning that the minimum number of neighbors to take into account for aggregation. K-nearest neighbor, which you will learn in the next lecture where we'll dig into theory, will try to find neighbors in a graph that looks similar to you. So if you have 4 users, then if 2 of the users are very similar to you, it will base its prediction based on these users. So if we implement this in our basic skeleton, we just call KNN basic, and again, if you do not have this or it is unresolved reference, remember that you need to import this from the surprise framework. And now we can run this algorithm, and as we see here, we have the previous result from our SVD with a mean of 1.22. Let's see if this will be better or worse. And we had a worse result for this, and this is kinda expected. And if you are wondering what all this is basically just each fold that is being calculated. So 1, 2, 3, 4, 5 folds. So we were expecting a worse result because KNN bases its prediction on other users' rated values, and if you go into the surprise framework, you can see that KNN is also, even with better dataset, performing worse than SVD. But again, it has its benefits, which we will talk upon in one of the next lectures. So what you can play around with here is minimum k neighbors. So let's see what the default is. If we go into KNN, min k, default is 1. So it will only take a minimum of 1 into consideration, meaning that it only at least have to have 1 to perform this, and this is of course very what could you say, this is expected, because if you didn't have anyone, then what should you base your prediction on? But if we try to switch out our dataset, because we don't have many users here, but we switch this out and go with the ML of 100k, and we change this to, let's first try run it without to see the result on this larger dataset. This will probably take a bit more to calculate because it's a slightly bigger dataset than our 4 users right here. So this was the first fold calculated, starting the next one, and in total we should have 5 folds because we are using cross-fold validation of 5. So now we have a result of 0.77, and let's try to change this parameter and say 10, and let's see what happens. And again we now have 0.77. So this is not the biggest change, or not a change at all, but that is also what you can experience with machine learning, that you try to fiddle around with these parameters and something work and something does not work. So it's really a thing that you have to play around with, and there's also some other things that you can play around with, but I will let that up to you. Remember, you can find all the parameters in this document and the different KNN you can use that is both user-based and item-based, and we will be talking about these two in the next lecture. I've implemented KNN in our little Python application. It's time to look at the theory behind the KNN that we have been using. Our KNN is using cosine similarity, and right here we have the algorithm or the mathematical formula for calculating the cosine similarity between user X and user Y, in this case user U and user V. So this is basically the mathematical formula. I will not talk much about this because you will probably not understand much of it, because this at first hand look very confusing and very difficult to understand, but in my next slide I will break it down and put in some values so it will become much more easy for you to understand. But an overview of cosine similarity can be seen in this formula, like this picture right here. So we basically have two users, the two dots right here, and then what we want to do with cosine similarity in KNN is to calculate the cosine angle between these two users, meaning that how similar are the users, and we are doing that for every user in our dataset. So we compare each user against each other to see how similar they are. And then when we know which users are similar to the user we want the prediction for, we then use this formula right here to predict the rating. So let's get into a more simple example. This is the cosine similarity and predicted rating formula breaking down with values. So this is similar to the one right here, but these are much more easy to understand. We'll be using the data from this table right here. So we have some users, we have some dishes, and they have given some ratings. So first we want to calculate the cosine similarity for user 1 and user 3. So what we do is we take the rated value for each of the items. So user 1 has rated pizza 4, then we multiply that with user 3's rating of pizza, which is 3, and then we plus for the next item, which is 2 and 3, and then when we get to our item that user 1 has not yet rated, we just insert a 0 and then multiply by 2, and then so on. So that will be done for every item that they have rated to see which one they have in common. Afterwards, we take the square root of each of the user's rating, so all user 1's rating, and then multiply it with all the ratings square root by user 3, and that gives us a similarity value of 0.9 for these two users. So this is how we calculate the cosine similarity in the KNN used in our framework. So now that we know how to calculate the cosine similarity, we'll move on to the predicted rating. So in order to calculate the predicted rating, we simply take the cosine similarity between the users based upon how many users we had set our mean to. So if we say that we need to have a minimum of k users set to 2, then we say for user 1 we calculated that his similarity, cosine similarity with user 3 was 0.9005, which is the value right here, and then we have calculated for one of the other users and found that it was 0.49. So our k mean is set to 2, so we compare these two users. Then we simply just take their cosine similarity and the first user multiplied by 1 plus the second multiplied by 2 divided by the value summarized, and then finally we get to this value that we can divide, and we get a final value of 1.64, and this value is the predicted rating for fish soup, which is the missing value right here for user 1. So this is done for every missing value for a user. So when a new user comes into the system, we calculate his cosine similarity towards the other users, and based on that we can start to calculate a predicted value for the missing ratings that our user have. This can be done both seen from an item perspective and a user perspective, where in the item perspective we focus solely on the items to see which items are in common, so we will be comparing items, whereas in the user-based approach we are looking at what users are similar to this user that we wish to calculate this for, and these two approaches are both supported in the Surprise KNN framework, and you can change in between them to see which one of them fits your data and your context the best. In the next lecture, we will be learning how we can change from a user-based approach to an item-based approach. So I will see you in the next lecture. We know that there is a user-based KNN and an item-based KNN. It's time for us to see how we can implement this in our code. So we will build upon our skeleton for KNN, and then we will create a variable and call it similarity options, short for sim options, and then we will say that name should be cosine, meaning that we're using cosine similarity to calculate the prediction, which we learned about in the previous lecture. And then we can define whether we want to be user based or not. We will set this to true, and then we simply one too much like this, and then we just to our KNN, so we say sim options equals our sim option variable, which is a dictionary. Now we can run our KNN, and it will be computing the 5 folds, and we should then have a result. So now that it is done computing, we have our result right here, and we have a mean of 0.8, and then we can try to set this to false, meaning that we will not be using a user-based approach but an item-based approach. So we will compute this. So now it is done computing, and as you see here, our result was a little bit worse than when we had the user-based approach. We now have 0.81, which is 0.01 worse than the user-based approach. So this is another parameter that you can play around with, and again you can go to the documentation page and see what is possible for you to do, because now we are using cosine similarity as our measure to predict the similarity between either users' items, but there are other approaches as well. So try around and see what you can get based on the result. You can either use this dataset or extend upon this little test dataset that we have made. So now that we have seen a theoretical perspective of the algorithms and we have tried implementing them and playing with the parameters, it's time to see a more useful setting where how we will be using the algorithms if we were to set going live with the algorithms. So let's say we want to make a social media service, and we want to use the KNN algorithm to try to predict users to one of our users that he will likely have something in common with, meaning that we want to present these users to him as possible friends that he could add to his friend list. So by using the KNN, we will set the user base to true, because we want this to be user based, because we want to present possible friends to him, and then we will be using our own little data set here to make it easier for us to understand the output, because we can quickly get an overview of what these values is. And then we need to add something to this. So first we will say algo.fit, and then say train set, and then we need to define a train set. So train set equals data dot build full train set, and then we simply say UID equals train set to inner UID, because the users that have this ID right here will not keep this user ID of 1, 2, or if this was name like Thomas or something, they will not keep this value when they get into the data frame. So we need to convert it into a user ID that our algorithm can understand. So we will try to predict some friends for user 2. So we say 2, and then the result here will be the inner value of user 2. So we then say predict equals algo dot get neighbors, and then we put the user, and then we say we have only 4 users, so we want to see the 2 most similar users to user 2, meaning that the 2 users that we will give him as output and say, hey, maybe you would like to be friend with these 2 people because you have a lot in common. So we just make a simple print, and then we print the result, and now we no longer want to use the cross validation. So we run this, and as you see, the users that he has most in common with is user 0 and user 2, and these are based on their inner ID. So we will just take the say transit dot to outer ID, and then say the first value in the predict, and print that. And then we have an error because this was raw ID. So the user that is most likely to be similar to our user 2 is our user 1. And let's see, user 2 has rated Harry Potter, and 1, 2, 3, 4, 5, 6, and Tomb Raider, and user 1 has rated Star Wars and Harry Potter. So our algorithm predict that due to the fact that both the users have rated Harry Potter and they have been rated really high on Harry Potter, they have both been rating these 2 movies 3. They are expected to have similar taste in movies. So this was a small example, and what you need to do now is, if you want to use this in an actual system when you have a live system going on, make a simple service that you can call and then give user ID as input, and then you can output this value or even more values by just looping over the raw IDs of the predicted inner IDs that our KNN algorithms present to you. Along in the last lecture, we took our KNN algorithm and tried to predict, given that we have a social media platform and wanted to recommend some users that our user 2 could be likely to add to his friend list, we were able to predict that the user 1 was a good candidate to present for our user 2, given that both of them has rated Harry Potter with a relatively high rating. So now we want to, instead of predicting a user in this fictionary social media platform, we want to recommend some content to our user 2. So we will see how likely it is that he will like Star Wars. So we need to change a bit in our code. This is the code from the last lecture. If you have not yet written it, revisit the previous lecture to understand what this is. But we will be deleting some of it, so like this one. Then we will keep this line. We will be changing this line. Instead of KNN basic, we'll be using SVD, singular value decomposition, and then we will be using this line as well. We don't need to transform this to an inner ID anymore, and therefore we don't need this line as well, because we are no longer working with KNN, so we have no neighbors to get. So we will say predict, and we want to predict for user 2 his predicted rating for the item Star Wars, because he has not yet rated Star Wars. So that should be all, and if you run this, you see the result right here. For user 2 on the item Star Wars, the predicted the estimation was 2.5. So he is estimated to give a rating of 2.5 on the item Star Wars. So Star Wars is an okay candidate to present given that our highest rating is 4. Let's see on Tomb Raider. Oh well, he has rated that, so we will just take, let's say, user 1. He has not yet rated Tomb Raider, so we will try that. Tomb Raider, and we will execute this. And that is a fairly good result as well. We are seeing that the values are more likely in the same rating scale, and they were not much different from the two users on the two items, and that is because our dataset is so small. The larger the dataset you get, the more accurate your value will be, and this can be illustrated if we take this line into consideration again and comment this one. Then we will also see, if you remember in the SVD, that we have a very bad MIE on this result. So this was a way to present estimated rating for users on items. Now we have seen how to use KNN to predict users that our user might be interested in due to similar features or similar habits, and we have used the SVD in this lecture to try to predict what a given user will rate a given item. In the next lecture, which is the last lecture, I will show you quickly how to set up a small REST service using the framework Flask in Python, such that you can from your web browser call your SVD algorithm and ask it for a prediction for a user on an item. So see you in the next lecture. This lecture we will be using the Python framework Flask to make a REST service such that we can call our SVD recommender from a URL, meaning a web browser. So what we have to do is create a new Python file, and we will call this main. Then we will say from Flask import Flask and request, and then we say from our recommender import, and let's call it do predict. So we just have to go in here and simply say do predict, and then we need to make the things that we are going to use. We'll be using this so we can clean up our code, and we'll be using this as well, this and this. We will not be using this one, and this as well, this, and we need to change a bit in our code, but we will do that afterwards, and we will simply just say return predict, and we remove this line as well, so like that. And main, now we have to do predict, is no longer an unresolved reference, so we will be making the app with the Flask. So we say name, and then we need to supply give the route that we are going to use to navigate to this resource. So we will say prediction as the first one, so we will have our URL, typically a IP address, then prediction slash, and then we will be using user ID, and we will be using item ID, and we need this one as well. And then we will say strict slashes equals false, and then we will say def predictions, which is our method that will be called once this URL has been passed. So we will say return do predict, and this one will take the user ID and the item ID and simply just pass it into our do predict method like this. And then we just have to say if name equals main. This is just some basic thing when we're using Flask. You don't need to worry about it. If you want to understand Flask fully, then you can Google and read up upon it. It's just a very simple thing that we are doing here, and it can be used in a much more complex way with get request and post request and a more RESTful approach. This is just a direct call with parameters in the URL. So we need to do like this, and then it is unresolved because we have yet to install the library. So we will find Flask, and it is right there. We will install it just as we did with NumPy and Surprise and Pandas in one of the first coding lectures of this course. So it's a similar approach we are using. And it is now installed, so we click like this and it will reload and refresh. We probably do not need, yeah, so we will go into recommender and let's see, we will take, it was user ID and item ID, and we will be giving this is the user ID and this will be the item ID like this, and then we should be good to go. And just go back here and let's try run it and see what happens. So we will be running the main now instead of the recommender, because we will do a call to the recommender file and use this method. So we will be navigating to the URL right here, and as you see here, it is not found because there's nothing listening on this exact specified URL on this port. So we will be saying predictions user 1 Star Wars, and let's see, there is an error. That might be because it is not concatenated, so I'll just do a quick test. What if I say Star Wars? Ah, wait a minute. Like this, and so the server encountered an error. So let's see. In make response, the view function did not return a valid response tuple. So we will just say return string, and we run this. Make the call, and as you see here, we now have this printed out in our browser. So if you had a service, you could call this entire result right here and then just take out the predicted or the estimated rating for user 1 on the item Star Wars. But you could also make it more sufficient with or efficient with a real post request, meaning that you do not need to have this in the URL, but will be in a body, post body instead. And then you could also sort in your output and just output the estimated value and maybe the item name. This is just a way that you can be using these algorithms, and I really hope that throughout this course you have gained some knowledge about machine learning and especially shallow learning algorithms. As I said in the start, this is nowhere the complete course that will make you an expert, because no single course can do that, but you are now on the right track and you have started your MI learning path, and you are now ready to experiment further with the algorithm from the Surprise library, or if you feel ready to be challenged even more, you can go on and look into deep learning and TensorFlow and what kind of cool things that you can do with that. So I hope you enjoyed the course, and I hope that I will see you in one of my other courses. So thank you for now, and see you.